Okay, good morning. Today is August the 2nd. This morning, I would like to start chapter 5. And today, this is just a descriptive session, basically. And in the second part of the session, I'm going to explain what are we going to do tomorrow. Okay, right now, I am at home, but immediately after this session, I will go to the university to check that everything it's ready for tomorrow. Okay, so that's the 2 points for this morning. Of course, at the end, if there are some issues, questions about the evaluation for this Thursday, yeah, I will try to answer those. Okay, let's get started. That's not what I want. That's not what I want. Okay, just can you see my full screen?
Yes, doctor.
So these are the 5 points for this chapter. Okay, we're going to start today, and in general, the structure of a ship is a very complex structure, very complex. Loading, the structure itself, geometry is very complex. So to try to analyze it directly as it is, it's the only possibility is just find an element. The problem is that it takes such a long time to develop a finite element model. You will see that next semester. That it is always a good idea to try to get a simplified version of this analysis. And we can do that applying this decomposition, okay? This decomposition means that we're going to consider that in 3 ways. First, that's going to come next, the 5th week. We will talk about the hull being considered as a beam, and that's what we call the primary behavior. And some of that are we'd like you to see at the lab. Secondary behavior, that's we see a reinforced panel. So that means that plating with reinforcements welded to the plate. And finally, the tertiary behavior is considering just a panel of plate, right? And that's basically chapter 4. The end, see, all of this is mostly longitudinal, in the longitudinal direction, basically. And 5.5 is just a common description of the response of the ship, but in a transverse direction. Okay, so basically it's a group of beams which are connected. Okay, as I said before, the structure of a ship is a very complex one. So I'm going to post this report from EAX. Okay, I'm going to write here what EAX means. It's a good idea for you to start learning about this terminology. Okay, EAX, what you see here, means International Association of Classification Societies. Okay, so it's some of the larger classification societies. They form this association, and it's EAX. So that means that if you heard the term EAX, that means that they are the more advanced classification societies, and usually means that they are more strict. Okay, For example, if you want to operate in the Gulf of Guayaquil, right? Since it's so sensitive, right? That means that if there could be some leak of oil or anything like that, it would cause a tremendous impact on the shrimp farms which are located in this area. So any vessel that operates in this area has to be classified by an IACS classification society. That tells you the importance of being IACS, right? And of course, you have the largest ones in here. For example, ABS, Lloyd's, DNV, RENA, and things like that. Now, this publication from IACS, as you can see, it's a glossary of terms, okay? And what I'm going to do for this in this class is you will see that I'm going to post this in the aula virtual, and I will ask you to review some of this terminology, right? So you will be responsible for reviewing the basic terminology on whole terms, okay? Not on whole survey, whole terms, okay? Let me show you just a little bit. Can you see the PDF, Daniela?
No, doctor, PDF not.
See if I can open it. Just to give you a short idea how this looks like. What is this? Chapter 5. Just to give you here it is. Okay. See, this is this publication, right? And this just presents, okay, a glossary, okay, a summary of terminology. And for example, I would like to show you just, you can see here the basic terms. And of course, you don't need to learn them. To do basically is give you, for example, one of these figures, right? Okay, and you will have to know what each one of these elements is, right? In this case, for example, this is for a single hull. I will explain in a few minutes what we mean by single hull, right? And yeah, you have all the terminology here. Okay, so you will be responsible for reviewing that. Okay, not now. I will give you a homework on that. Okay, that's that. Okay, now in this session, I'm going to start talking about general things about the hull of a ship, hull structure of a ship. Okay, and that's the idea behind today's session. Okay, first, probably you have heard the terms single and double hull. Okay, what do we mean by that? Okay, and this is what we mean. Okay, this is single hull. That means that you have the plating and you have cargo inside. And when you talk about double hull, you see that there is an outside, called this outer skin, and there is also an inner skin, right? So this space here, okay, it's in some cases it's used to carry ballast water, right? So for example, when a tanker delivers its cargo, okay, the draft is very small, low, So to increase the draft, you put water, ballast water in this tank. Okay. If in this case you suffer a puncture on the hull, you will have a leakage. If you suffer a puncture in this case in the double hull, nothing happens. Just seawater comes inside, and that's all. Okay. Damage has to be very large, this height, in order to reach the cargo tanks. Okay, that provides an extra safety to avoid these contaminations. Okay. In some cases, they don't build this one here, double hull, but they just build it up to here. Okay, for example, you have something like this. It's the hull, and they just build it this part here. Okay, a double bottom. Of course, this double hull provides safety not only on the bottom but also on the side. In this case, you have only protection if you have punctures on the bottom, not on the sides, obviously. So, but in this case, of course, the reduction in capacity of cargo transportation is reduced, obviously, right? This figure is also in your class notes. You can see the double bottom, right? Like this one here. And the problem here is that you can imagine, right? You have here a longitudinal element, right? It's welded to the plate. But somebody has to check that this welding is well developed, right? So that means that somebody has to come into this space in order to check. And this person who gets into here, it's you, eventually. So that means what I'm trying to say is that it's a compromise, because if you design a ship with a small height in double hull or double bottom, right? The spacing here is going to be very restricted, very small. So it's going to be very difficult for the welders or for the engineers who had to check this work. Okay, that's not going to be easy to do this checking. Okay, so that's single hull, that's double hull, this is double bottom, double bottom. Okay, so you start learning about terminology that we need. Okay, let's go on now. One thing which is very important is that there are two ways to build the structure of a ship. Okay, that's what we call the framing systems. Okay, framing systems. We define two framing systems, but in general, they are not usually chosen just like that, radical. Usually what they do is some sort of combination of the two, because both have some advantages. Okay, so in one case, you see that the girders support, well, I'm sorry, this is general terminology. This is the way which we should have in our mind, okay? The girders, that's the terminology that we have presented before. They support the stiffeners, right? So the stiffeners are the reinforcements which are smaller, and they are supported by the girders. The girders are the larger, they are supported by the bulkheads or the ship sides. Now, you could have girders in the longitudinal or in the transversal direction. And at the same token, you could have stiffeners in the longitudinal and also in the transverse direction. And according to that, you define two framing systems, okay? And these two framing systems are, as in the left, longitudinal, and on the right, transverse system, okay? So here, we consider that this is the direction fore and aft. Okay, so this is the X direction, okay? In the longitudinal system, I've drawn with double line the stronger elements. So these are the girders. Okay, so this, and that, girders. And these smaller are the stiffeners. Okay, so when we talk about longitudinal framing system, okay, the girders, they go in the transfer direction. You know, and the longitudinals, these are the stiffener, these are the smaller, they go in the X direction. Okay, you see immediately that this is spacing, okay, this is spacing between girders. In stiffeners. You see immediately that the girders, since they are stronger, they are located a larger spacing between them. Okay? I think that you should always try to see when you go and visit the structure of a ship is take a quick look at these things. Is this, what type of framing does they employ? The spacing between girders, the spacing between stiffeners. Okay? At the end of the girders, okay, since they are stronger, they are supporting, they are receiving the load from the stiffeners. They have to transmit that load to another element. Okay? And that's what we see here, to the bulkheads or the ship sides. Now, so it's always a good idea that, okay, you have a very strong element and it's connected to another strong element on the bulkhead. So it's a good idea that you learn how this connection is being completed. Okay. Other very interesting thing is that when you go and visit, is that the spacings. Because these parameters influence eventually on the weight of the structure. And of course, you always want a lighter structure, right? Because it's cheaper. Okay. Now, on the right-hand side, I'm showing you in a very simple way the transfer system. Okay. So again, you have this double line. These are the girders. Okay, and here, these are the smaller. These are the stiffeners. Okay, so the pressure, for example, acting on the plate, okay, and the plating are being supported by the stiffeners. It's like saying the load is transmitted from the plating to the stiffeners. The stiffeners are supported by the girders. It's similar to say that the stiffeners are transmitting the load to the girders. So the girders take the load from the plating, from the stiffeners, and transmit it to the very strong elements, which are the sides of the ship or the bulkheads. Okay, so at the beginning, it's going to be a little bit difficult to remember, but yeah, okay. Longitudinal framing system, that means that you have very strong transversal elements. And the longitudinal are going to be very small, and they're going to be closely spaced between them. The contrary is transfer framing system. Okay. Now, to select that, there are several considerations that people make or engineers make, right? In a few seconds, I'm going to show you two figures or two plans from fishing vessels. One of those is built with the longitudinal, and the other is built with the transverse framing systems. That means that eventually it's not only matter of the utility for the ship owner, but also the experience from the ship yard. Okay, for example, if they have more experience building ships with this type of framing, they will, of course, this experience make things easier for them. So, but anyway, here we have some consideration. Now, there is a publication, a very old publication from Professor De Arcangelo. I'm going to write it here just in case you need some time in the future. De Arcangelo. It's a very old publication from Snaney. Okay, and they basically what Professor De Arcangelo did was he considered different type of ships, and he was giving you a summary of the positives and negative things about framing systems. So you have a general idea why this, why that. Take a quick review of that, and that will help you. Or otherwise, when you go to visit a shipyard or a ship, try to check that, right? For example, if you have a very high element, that means that the spacing above this element is going to be reduced. And you don't want that, right? Because you want the largest space to carry load, because with cargo, because with carrying cargo, the ship owner makes money. That's what he wants. Okay, so that was one of the first things that we have to have. Okay, cargo handling and use of the interior space. It's possible that you have, like it says here, special requirements from load, right? There are some special requirements that it's any special load, shape or geometry. So you better build the ship with longitudinal or transverse framing system, or ease of construction. Right? For example, there are certain shipyards who prefer, because they have more experience with this or that. Okay, so, and another thing which is very important is maintenance. We all have a general idea that we work with seawater, and that produces a lot of corrosion. So that means that you have to have in mind that, yeah, you have to build it. You have to design it, you have to build it. But then after a few months or years, you have to give it maintenance. So you have to keep that in your mind when you design something. Okay? So that's that. Here, for example, I'm going to show you the plans of two fishing vessels. They both operate here. Okay, but that doesn't mean they were built in Ecuador. They were probably built somewhere else. But anyway, they are operating here. So this is both are steel. Okay, this is you see that there is a longitudinal, the transverse, very strong transverse, and the longitudinals are very small. See, basically the longitudinal, you see that this is just a flat bar. See, this is a flat bar. So this is just a small element. And the transverse, you see, it goes from here to here. And still, it has a flange. So the transfer is much, much, much stronger than the longitudinal. So this is a longitudinal framing system. Okay, this is a it's a fishing vessel. Okay, now here, this is a Doña Tula. Check for the height of the transverse elements. And here, you can check the height of the longitudinal elements. So this the girders. So it is possible that, for example, here you have a round beach. Here you have chines. So it's possible that that affected the selection of the framing system. But in general, I don't know if you can see the girder. It says 9 inches. Ms. Arechua, could you please turn on your cameras? Everybody turn on your cameras, because I want you to show me with your fingers. How high is 9 inches? Can you show me 9 inches with your fingers? Ms. Flores, can you show me 9 inches? It's like this, or like that? No, 1 inch is like that. It's 2.54. So 9 of those is about that. So it's a very strong element. Okay, so that's what I want you to keep in your mind. Okay, it's not just a matter of watching these things. No, it's just having a physical idea of that. For example, on the left-hand side, see here. Okay, here. You see that from this here, it's 150. So that's millimeters. So it's about 15 centimeters, about this high. This ship is smaller than this one. So it's a good idea for you to start getting physics into that. Okay, and it's a combination. See here, it says 150, those are millimeters, 90, that's the flange, and then you have 3/8. These are inches. You see, it's a combination. So that's why we always have to go from one system to the other. So you have to start practicing from now. Okay, you are not going to find one single system of units. They are both mixed up. So we have to start worrying about that. Okay, I don't know if I can find the dimension of the longitudinal. There's no longitudinal here. It's not the dimension. Okay, 3/8. How much is 3/8 in millimeters, people? Okay, 2/8, that's 1/4. It's a little bit above 6 millimeters. So 3/8, it's about 8 or something millimeters. So that's a good plating. So it's always a good idea for you to start looking at those details, not just okay, yes, I can do it without AutoCAD. No, start making some sense, physical sense in your head. Okay, and before we leave here, you can see here, that's 5/16. That's the thickness on the side. 5/16. That's, it's a little bit below this one. Yeah, because remember that probably the water is up to here. So up here, the pressure is not so high. It's basically above the water line. So those things have to start making some sense in your head. Okay? So longitudinal framing system, in that case, you have the longitudinals are very small, shortly spaced between them. Transverse are very strong girders. Okay? There's another example here, for example. Okay? In this case, we have longitudinal framed double bottom. Okay, you see that this is the top of the double bottom. Okay, and in here you see that you have this. Sorry, this is transversely. Okay, you have these longitudinal elements, very strong elements. And in this direction, you have the transverse. Now, here, you have the center girder, right? And you have these elements here on this side to keep it straight, to keep it vertical. So all of this helps you, because remember that when the ship goes into the dry dock, okay, it sits on blocks, and that provides a very strong load in the vertical direction. Okay, so you see that these are very small elements compared with the longitudinals. This is longitudinal framed system. Okay, so basically it's the same ship. This is the one version of the system. This is another version of the same structure. And here you see that these are the longitudinals, and there's the spacing between them is much smaller. Something which is very interesting is that even though this is a longitudinal framing system, right? You see here that this is a very strong longitudinal. I have found that there is a maximum distance between this and that you have to have. Okay? So if you have more than, I think it's 2.5 meters, then you have to include an intercostal side girder, even though this is a longitudinal framing system. Okay, so you have the center girder, and then you have this, and this spacing cannot be larger than, that depends on the classification society, but I think it's 2.5 meters. Okay, so you immediately see that this spacing is much larger, not smaller than this one here, from here to here. And again, this transverse, similar to this one here, it helps the vertical element to keep vertical. It doesn't buckle to any direction. Okay. So you have here two versions of the same ship, basically. This could be a tanker. So this is very interesting. I can give you a couple of seconds to identify the type of framing that you have here and here. What type of framing do you have here on the side, Mr. Zurita? What do you say on the side?
Un momento, doctor. 8. I can see 8.
Yeah, but you can look it up in your class notes. It is in your class notes. You see the transfers are very close. See, this spacing is very small. If you had to say something, would you please give me a dimension for this spacing, more or less? How much do you think it would be? Just from the picture. Mr. Guaman, could you give me a spacing for this, the dimension for this spacing, number for this spacing?
Maybe 80 centimeters.
Something like that. And how about the distance from here to here? Here to here. You see that in this case, this deck, this is an internal deck, is basically the longitudinal girder for the side. This deck is basically the longitudinal girder for the side structure. You have This is the girder, and the other direction, these are the framing on the side. Here on the bottom, what can you say? Any characteristic on the bottom? Well, you have a double bottom here, right? Mr. Tenemea, any characteristic of the double bottom? Mr.
Well,
Tenemea,
is the girder is very long.
very strong, right? In the longitudinals, how about the longitudinals? Are very small. So this is longitudinal framed system. This is transfer framing system. And how about the deck? Mr. Hidro, what can you say about the deck structure?
Good morning, doctor. It's a longitudinal framed also.
Exactly. So you have longitudinal, transverse, longitudinal. So it's a mix up. Why they did that? I don't know. Maybe they found specific advantages for building this thing in this way.
Doctor, and
Yeah.
in the internal deck is also the longitudinal in the internal deck.
I cannot see below here, but probably it's transverse also. Because probably they install a transverse at the same position as the transverse in the side. So from here, they have a stiffener. From here, another stiffener. And from each one of these, they have a stiffener. And you see that this is very strong. This is longitudinal direction. So probably this is also a transverse, probably. I cannot see quite clear the details.
Excuse me, doctor, I got a question. Why do some structure have holes in the corners? I don't know how to say it in English, but is
This
aligeramientos?
Yeah. Well, there's several reasons. Okay. For example, here, okay, you need to weld, right? The two plates you need to weld. And that welding has to be continuous in order to avoid leakage. It's very difficult that you are sure that the welding is continuous. So you have, in this case, you have to include some lighting.
Okay.
In this case here, it's different. In this case, it's just to save some weight. And also, okay, for example, if you want to use this space for ballast, right? So you pump water, seawater. But this water has to be located in the whole space. So you have to leave the holes so the water can flow from one space to the next. Finally, for example, in this case, I don't know, they're gonna use it as a double bottom, but you immediately see that this is very restricted space, right? For example, if you have to paint this, right? Or you have to change one of these stiffeners. So you have to go inside and from one space to the next one. So you need these holes in order to go to the place where you want to go. For this is probably you need to apply the classification rules. They tell you in detail how much is the sliding. Okay, Mr. Mendez?
Yes, doctor.
Yeah, you have to be patient for that. We are not going to work on that. You work on that in metallic construction. Then you have to go and for example, design one of these connections. Brackets. Okay. If you see that according to the size of the bracket, the unsupported length is affected. So if you have a beam, right, the length of the beam to the square, it's proportional to the bending moment. So if you reduce this length by 10%, that means that you reduce the bending moment by 20%. So it's a good idea for you to take a quick, nice detail of this design. But you have to be careful, because if you make a very large corner here, the space inside will be reduced. So if you design a very large bracket here, the space inside is reduced. And you have to remember that what you need is space to carry cargo. So yeah, these details will be reviewed in metallic constructions. That's the idea. Okay. Now, you have a general idea. Hopefully, I mean, hope we could make a quick visit, but we still have problems with visiting shipyards. But anyway, when you go and do the practices, professional practices, you start taking quick looks to that, okay? When you see, go and visit, not just to see the, okay, no, try to start making some sense out of it. For example, the first thing that you have to do is try to determine, is this framing, what's the framing system? Is it the same on the deck, side and bottom? Try to imagine, okay? For example, okay, you carry cargo here. Okay, it is possible that the geometry of the cargo influenced the selection of the framing system. Only that, okay, so you have longitudinal framing system, okay, and you start seeing more or less the spacing between longitudinal is about maybe 60 centimeters. You start learning from there. It's not just it's a visit, it's just a technical visit. Try to learn from that. Again, similarly, what's the spacing between girders? And you have a girder is a strong element. So you see that the strong element goes up to the bulkhead. Fine, but in the bulkhead, you have to prepare a very strong connection, right? Try to learn from, okay, how it is connected to the vertical reinforcements of the bulkhead. Similarly, on the side, right? On the side, it's possible that you have a strong element. How it is connected to the longitudinal, to the bulkhead. See, those are the things that you should see when you make a visit. It's not a social event, it's a technical event. Okay, let's go on. At the beginning of this session, I said that similarly with the thicknesses, for example, I called your attention to the values of the thickness. So you start, okay, every time you see a plan, at least you should come out, okay, taking a physical view of the spacings, of the height, and also the thicknesses. The minimum thing that you need to after you get it from a visit. Because every time you have to calculate something, you calculate, for example, the thickness of the bottom of the structure. And you calculate and say, okay, I'm going to need 12 millimeters. 12 millimeters is a very thick plate. Does that make sense? If you go and visit, okay, you say, okay, this is a 100-meter long ship. And in the bottom, they have 11 millimeters. They start making some sense. So you have a 60-meter long ship. I wouldn't expect to have 12 millimeters. That's the gain, your personal gain, when you go and make a visit. Not just, I get out of the class. No, try to gain spacing, height, flange, thicknesses. So when you have to calculate, see, you start calculating, yeah, you apply the rules, but you have a rough idea how much is going to be the result. We cannot teach you that. That's experience. So you have to take advantage of the visit, every visit, to gain. Okay. So we're going to explain how can we decompose, okay, the structure of a ship. For example, I'll give you this. Analyze it. I will start crying, because how can I analyze this? So this is what we can do. What we can do is think that the ship, the structure of a ship, can be decomposed in certain behaviors. Okay? The first one is the primary behavior. Okay? So for example, you see a plan of a ship, and you see that this is something very long compared with the depth or the width of the beam. So something very long, that's a beam. That's a beam. So what we do is, okay, let's consider first that the hull is a beam. And that's what we call the primary behavior of the ship hull. Of course, the section is not constant, because at the forward end, the section is like that. In the central part, the section is like this. And the aft, the section is like this, and it's a little bit higher. So immediately you can see that the inertia, it will change from the forward end to the aft. It's not going to be constant. Okay? And that's what I want you to do tomorrow. To take a simplified, of course, simplified analysis of this problem. Hull beam. Okay? The other one is, okay, let's get closer to the structure. And let me go back here. Okay? And you see in this area that you have plating and you have longitudinals. Okay? Or for example, here, you have longitudinals, plating, and you have transverse. So that's what we call a secondary structure. So it's plating plus stiffness. So in this case, the plating is forming the flanges of the reinforcements. See? And remember, for that, we need to use the concept of effective breadth. Okay? So you have the longitudinal or the transverse, you have plating. So the plating is the flange. How much is this width? That's the effective breadth. So you calculate the theory of shading or the regulation from the Classification Society, and the two elements together, they bend. And then, of course, they develop some stresses. And finally, the tertiary behavior. Okay, in this case, see, you have plating, longitudinals, or transverse, and you consider only the plating between these elements. Remember, please remember, when we talk about secondary, and that's something that we explain at the end of chapter 4. In this case, okay, the plating is welded to the stiffener or to the girder. But in the thickness, okay, the normal stress we consider as uniform. In the tertiary behavior, okay, you have the plate and it bends. And in this case, in the thickness, the normal stress changes linearly. That's what we call the kinematic hypothesis. So on the top, for example, you have positive. On the bottom, you have negative stress. And that's a linear variation between them. That's the result of the kinematic hypothesis. Okay? Now, you can immediately think, in just a second, but the primary develops some normal stresses in the x direction. In the case of the secondary, if you have something like this, right, probably the neutral axis will be much closer to the plating than at the flange of the reinforcement. Why? Because the plating is so large. So the stresses usually at the flange are larger. Okay? If these stresses come in the longitudinal direction, that means that the primary and secondary stresses will be combined. So that's why we need to have a clear idea how the structure is being supported. Okay? That's why we need to have a clear idea what elements are in the longitudinal and in the transverse directions. Okay, and finally, for the tertiary, okay, remember to have a discussion at the end of chapter 4. The main problem here is that if you give me the boundary conditions, the supports of the edges, okay, yeah, I could apply Timoshenko, apply another. The problem is that in this case, the edges are neither simply supported nor clamped. Because when you have a plating and the stiffeners, you apply the load, the stiffeners, they deflect. And also probably they rotate a little bit. So they here, you have the plating, you apply the force, and they deform. So they are neither simply supported nor clamped. If they were clamped, then the bending moment close to the boundaries, the edges will be about twice the value at the center. When you have a uniformly distributed load, more or less. But when you have this redistribution, because the stiffeners bend a little bit, more or less, you have about the same stress on the side that at the center. They have different sign, remember? The curvature is like this and like that. More or less, the values are about the same. Okay, so you see the connection between what we have studied before and what we are going to study now. So that's why, I mean, this course is so packed, very well connected. Okay. Now here, this is the results of the whole bending, okay? For example, here you see immediately that about here, you have the largest bending moment. And in this case, probably because corrosion, fatigue, there are some cracks, and they reduce the strength, longitudinal strength of the ship. And eventually, these accidents happen. Okay? This is the secondary. For example, in this case, I'm showing you this is in one direction, and these are longitudinals in the other direction. This is spacing. This is smaller than this spacing. And you see that this height is much higher than this one. Okay, so if I apply load to this, yeah, the combination of these two will bend. Usually, in the flanges of both longitudinal and transversals, we will have the largest normal stresses. And finally, well, this is a model. And finally, if we consider this space, this plate between longitudinal and transversals, it's basically a rectangular plate, isotropic, and we can apply load and we can find the normal stress distribution. So we're going to have these three behaviors combining. And the problem is that we have to be careful because in some directions, X and Y, there could be some combination of stresses. And that's why we usually do not try to compare with 235. Why not? Because when you consider, for example, just the primary hull, yeah, okay, you have longitudinal stresses. Yeah, but this element, the plating, for example, we're going to bend. And when it bends, it develops also tertiary stresses. So you have to combine the two. Okay, so that's why we do not, when you see the permissible stresses in the classification rules, they are never 235. Or just in very few cases, they could be something like that. But in general, they are below that. Why? Because we have a combination of these three. People, is there any questions about this? Any questions about this? So for the first behavior, primary, basically we have normal and also shear stresses. And basically that's a whole beam. For the second case, we could have to consider reinforcement in two directions. And what we can do is we can model that as a group of stiffeners, just beams. It's what we call a grillage. And then we apply the load. Now, for the inertia of each one of these beams, we need to consider the effective breadth. And finally, for the tertiary, it's just chapter 4. You have a plating, apply load, and it bends. On the top and on the bottom, in the tertiary, the stress is going to be opposite, the same but opposite sign.
Doctor, I have a question.
Yeah, go on.
On the secondary, we have to take like each girder is a beam and deduce the stress for this beam.
Yeah. Yeah.
And what happened with the stiffeners?
Same. But you have to be careful because in this case, the directions are not the same. See, for example, let's consider this stiffener. Okay, in this case, you're going to have a bending moment like this. So you're going to have on the flange normal stresses in this direction. On the girder, you're going to have a bending moment like this. And the stresses is going to be in this direction. This is normal to that, orthogonal to that. Ms. Santos?
So we will deduce or resolve that problem like the homework that you sent at the first semester when the beam was on the other beam and have the reaction between that.
Yeah. See, there was an example. I don't remember. I think it was something like this. Something like this, and you have a force here. So you have this long beam, and you have this simply supported beam with a load here. Yeah. So basically, that's a grillage because you have two beams supporting a force normal to the plane of the beams. Yeah. The problem is that here you have only two. In here, you have many. So the process to analyze this is more complex. Santos?
Okay, thank you.
Yeah, but my message here is that we have to be very careful with the directions. Okay, we have to be very careful, and that's related to the framing system. That's what we said in chapter 4 about the bending, right? If you have a plating which is like this, in this direction we have the largest bending moment. But we have another ship which is designed with, so this is X, this is Y. This would be a panel in the longitudinal framed ship. This would be a panel with a transfer framing system. In this case, you would have the largest bending moment in this direction. So in this case, okay, the tertiary bending will be in the Y direction. And in this case, the tertiary bending will be in the X direction. So you have to have a clear idea of the physical situation. Okay, so in this case, in this example, if you have longitudinal bending, the primary bending, you will generate stresses in the X direction. So for this example, these stresses here will be acting in this direction, while the tertiary will be in the Y direction. So the combination is going to be special. We're going to present something that we call a failure criteria. And in this case, it's a von Mises criterion. I don't know, maybe you have heard. In this case, the tertiary stresses will be in the X direction. So they will combine directly to the normal stresses from the whole primary hull beam.
So we will select the maximum normal stress for each
Always. That's something that we always should do. I mean, in some cases, right, you can say, okay, I expect the maximum stresses to be here or there. Yeah, if you are a very old person with a lot of experience, yeah, you can immediately go and analyze in this point, and that's all what you need to analyze. When we are younger, including me, what we need to do is to analyze the stresses in many positions, and then confirm that even in the largest in the position where you have the largest normal stress, that's below the permissible stress. So it's yeah, you can try to save some time, but it's always a good idea to do the checking. The stresses in several positions and check that in all of them, the structure is safe. Santos? Okay, people. Mr. Dominguez, you have a question?
Yeah, doctor, good morning. The lot will be the same in the three cases.
They are related. They are related. For example, in the case of the hull beam, right? This is something that we are going to do tomorrow in the lab. Okay, let's suppose it's floating about here. You have pressure here, right? Okay, so this pressure, we are going to consider that as force per unit length on the whole beam. Okay, this is X and this is Z. So here we're going to consider a P of X. And this P of X is related to this pressure. but it's not exactly the same. Because remember, this is force per unit length. But yeah, it's related. But now, if you want to analyze the panel of the bottom, yeah, in that case, you apply the same pressure to analyze this, if this were the bottom panel. And if you analyze the plating, yes, it would be the same pressure. But here, as a primary, the pressure has to be seen as the behavior, since this is a beam behavior, as a force, so it has to be converted as a force per unit length. And here, they can be taken directly as force per unit area. So they are related, but they're not the same. Mr. Dominguez?
Yes, doctor, thank you.
Okay, people. Daniela, would you please stop the recording?
Okay, doctor.
So